So let's say we wanted to evaluate this integral x, the integral of x sine of x dx. Well, we could do these separately. I mean, we could easily do the integral of x or the integral of sine of x, or basic integration rules, but when we multiply these together, unfortunately the properties of integrals don't allow us to sort of separate these out, take their integrals separately, and then multiply them again. So fortunately it's going to be a little bit trickier than this. So we can't use our basic rules at this. So if you can't use your basic rule, next tool you should pull your toolbox and see if it works should be use substitution. So let's give that a shot here. Let's just say u equals sine of x. Next step in the process is determine du dx. In this case, that's just cosine of x. Now we solve for dx, which is 1 over cosine of x times du. And now we can go ahead and evaluate this integral by plugging in for the dx and the u that we just solved for. So first we take our u and plug that in for sine of x, and we can take that dx that we found and plug it in for dx up here, and we plug those in and we get the integral of x times u times 1 over cosine of x times du. And unfortunately this is a brick wall. And it's a brick wall because we're integrating with respect to u, but we've got two different variables in here. We got x and we got u's in here, and u is a function of x, so this is just really messy. We can't integrate this. It's not going to work. And the reason I want to just show this is because you're going to use the wrong method a lot, and that's okay. You're going to hit a brick wall. You just move on to another method, and it's important to actually go through this process where you're using a method that doesn't work, because that's how you learn how to pick the right use, to pick the right method, and that's how you learn to integrate quickly. If you run into a brick wall like this while you're working out problems, that's actually good. You're learning. It's part of the process. It may not be good as far as how quickly you're finishing your problem, but it's good for your learning. So use substitution is not going to work. So what can we try? Well, if basic integration techniques don't work, and if use substitution doesn't work, then your next step, you're going to want to try integration by parts. And integration by parts is based on the product rule. In fact, you could say that the chain rule is to use substitution, as the product rule is to integration by parts. So let's take a look back at the product rule. So we have the derivative of two functions multiplied by each other, assuming that u and v are both a function of x, is going to be equal to the derivative of that first function u times v plus u times the derivative of v with respect to x. So this is what the integration by parts is based on, and we just start off with this product rule, and we just do a couple manipulations to it, and we can arrive pretty quickly at our integration by parts formula. So first thing we want to do is just multiply each side by dx. Valid move, just like we did for u substitution. And we're going to kind of take this whole quantity here and multiply that by dx. Okay, a couple more manipulations to come here. But first, as you can see here, we keep that left the same, but on the right side of our formula here, we can cancel out some dx's, right? So we're just left with du times v plus u times dv. And now we can, just like we did with u substitution in deriving that, we can take the integral of both sides. So we'll take the integral of this side and integrate this side, and that equality is still going to hold because we just did the same thing to both sides. Now, on the left side, we can simplify this according to the fundamental theorem of calculus part 1. So if you take the derivative of a function and then take the integral of it, you just get right back to that initial function. So using this property, that left side just becomes u times v. So that simplifies pretty easily. The right side, we can split it out too based on the properties of the integral, and call it the integral of du times v plus the integral of u times dv. And we're almost there. We're almost to integration by parts. We just got a couple more things. Let's just subtract by that integral of v du on both sides. So now we've basically arrived. We're just going to switch the order around, and you could see this this du is a little bit out of place. Typically that's going to be on the right side, and we're just going to make this we're just going to switch this right side over to the left, which is just a little bit easier way to look at this. So we end up with the integral of u times dv equals uv minus the integral of v times du. This is our formula for integration by parts. It is something that you definitely want to remember. Hopefully you can understand the product rule, you're going to appreciate this much more, and you'll just have a really clear understanding of where it comes from. But this is definitely something that you're going to want to memorize. The U substitution formula is not quite as important because you don't really use that formula, but this, you will use the integration by parts formula. You have to basically plug right into this formula. And just looking at this, you may be curious, like, how is this even useful? Because I just have an integral on the left. If I'm trying to solve for this integral on the left, I go from one integral here, now I've got this integral plus this other value here, so how does that even help me? Well, in a lot of cases it's not going to help you, but in certain cases, if you pick the right U, it does help. So let's try this out on a problem. So when you're solving a problem like this, you're going to want to make some kind of a table. You got to pick your U, pick your dV, and then solve for du and solve for v. So let's make a little table here. First we want to pick our u, then we're going to pick dv, then we're going to solve for du, then we're going to solve for v. And once we solve for those, it's just a matter of plugging all those into our formula here and evaluating it, and hopefully when we plug it in, it gets us to something simpler than what we started with, such as this formula up here. So let's go ahead and arbitrarily pick a u. Let's just say u is sine of x. Alright, so I'm bracketing here in the red, and I'm going to call u sine of x. And then if that's our u, then basically everything else is our dv. So x dx is going to be our dv. So we picked our u, we picked our dv, now we can go ahead and solve for du. Du in this case is just going to be cosine of x dx. And our v is going to be our integral of dv. And so we can just go ahead and plug that in. It's the integral of x dx, which is going to be x squared over 2. So now we've got our u, our dv, our du, our v, and we're ready to go ahead and plug this into our formula. So let's just write it above our formula here on the bottom. So our first, we have the integral of sine of x, which was our u, and multiplied by x dx, which was our dv, which is just this formula down here. And we're going to set that equal to our u times v. So this is our v up here that we're plugging in. And then we're going to subtract from that the integral of our v, we're throwing in up here, times our du, which we got over here. So basically we're just plugging these values in. And now we can kind of take a look back at what we just did. In order to solve this integral here on the left, we need to know this integral here on the right. And this actually is more complicated than with the integral that we started with. So this actually isn't going to work. So yes, I just showed you a process here that doesn't work. And why would I show you that? Well, again, you're going to hit a brick wall like this often, and it's okay. It's just part of the process. And what I wanted to be clear with here is that it's really important what u that you pick. And the reason that this doesn't help us is because when I find du here, it doesn't get any simpler, and now I've got to integrate that du. And further than that, when I took the integral of my dv, it got more complicated too. So I'm ending up with a more complicated integral here because I chose the wrong u. So really our problem, we didn't have the wrong method, we had the wrong u here. So basic rule you're going to want to follow when finding u is pick the function out of your integrand up here. Pick the function that when you take its derivative to find du actually gets simpler. In this case, our du did not get simpler, and we hit a brick wall. And it's okay if you hit that, and it'll help you learn the process. So that's why I just wanted to show you this to know it's okay. If you pick the wrong process, it's okay. You just got to try it again. Try something else. So let's try this again. So our u last time didn't work. So let's give this another shot. So again, we got to find u, we got to find our dv, we got to solve for our du, and then solve for our v. Now, our u we picked last time didn't work, so let's try something else. Let's say u equals x. And then if that's our u, then our dv is basically going to be everything else. Now we got our u, we can solve for du, which in this case becomes 1. So you can see now you can tell we're kind of on the right track because our du got simpler. When we differentiated du, it got simpler. That's what you want to see. And another thing that you want to see is when you integrate dv, as we're doing here, the integral of sine of x, that didn't get any more complicated, really. I mean, maybe you could say a negative sign is a little more complicated, but cosine of x isn't more complicated than sine of x. So If you see a du that's getting simpler and a v that's not getting any harder, then you know you're on the right track. So let's go ahead and bring this formula up here just so we can kind of work down from it. And we're going to go ahead and plug in for the left side. So we plug in our u, which is x, and our dv, which is sine of x. Now that is going to be equal to u times v. So we plug in our u, plug in our v, minus the integral of our v times du, and we plug in our v and we plug in our du. And you notice now this integral here is, this should make you happy because you can see that we can actually solve this now. That 1 makes this really simple. So this part just becomes negative x times cosine of x when you multiply those together. And we can just kind of cancel out those negative signs as a first step. So we just end up with the integral of cosine of x dx, which we can evaluate. And this is sort of the whole point of integration by parts in all the methods that we do to find integrals. It's taking a complicated integral like x times sine of x, and we're taking one that we can't solve with basic rules, and we're manipulating it to the point where we get to an integral that we can solve. And now at this point, integral of cosine of x we can solve. So we've accomplished our goal here. We've reduced a complicated integrand into an integrand that we can find the integral for. So the left just is negative x times cosine of x, and that integral of cosine of x just becomes sine of x. And this is going to be our final answer. So this is how you use integration by parts to reduce a complicated integrand into one that you can actually integrate. And now a good thing to do once you get your answers is to go ahead and check it. So let's do that. So if you'd like to stick with me, let's go ahead and take the derivative of our answer and see if it matches our integrand. So this was our answer here. If we take the derivative of this, we should get our initial integrand here, if it is actually the correct answer. So we want the derivative of our answer here. And I'm going to put that second term in blue just so we can kind of follow it a little better. And so properties of differentiation, these are different. You can split up these different terms into two different derivatives. So we have the derivative, this is equal to derivative of that first term plus the derivative of that second term. So let's evaluate that second term quickly here. So the derivative of sine of x with respect to x is pretty easy. That's just going to be cosine of x. Now the derivative of that other term is a little bit more complicated. We're going to have to actually use the product rule in this case. So derivative of negative x times cosine of x is going to be the derivative of f times g, where we're calling that f is going to be that negative x and the g is going to be cosine of x, because it's two different functions. It's two different function types. We're going to have to split these up and use the product rule, which gives us this formula we discussed earlier. So let's define our f and our g. Our f is what's in the green, our g is what's in the orange. So easily find our f prime is negative 1, and our g prime is just going to be negative sine of x. So now we can just go ahead and plug these in for that derivative. So our f prime times g is going to be negative 1 times cosine of x. And then we add our f times g prime, which is negative x times negative sine of x. And simplifying these a little bit, we end up with negative cosine of x plus x sine of x. Now we can go back over here on the left and finally solve for this derivative here. So this first term over here in the black is going to become this, and this derivative here in the blue is going to become cosine of x, which we solve for up here. So we add that onto the end, and we can see at this point that these cosine of x are just going to cancel out, and we're left with x sine of x. This is our derivative of the answer we found, and we find now that that derivative of our answer equals the integrand of our initial function, thereby confirming that we did indeed use integration by parts properly and get the correct answer. So this is something you may want to do if you got the time to check and you really want to confirm that your answer is correct. If you use integration by parts to find the integral, you'll have to use the product rule to find the derivative of your answer to check it. And I hope this helps you to see how the product rule sort of undoes integration by parts, or how integration by parts undoes the product rule. They have this sort of inverse relationship, not too dissimilar from the relationship between integration and differentiation, how each of those processes undoes the other.